Okay, let's now talk more about getting the frequency response. I always start off with the wrong color pen. Response from pole zero diagrams. And what we're going to do now is compare how you do this with discrete time against continuous time. We've already spent a bunch of time talking about this in class for discrete time, but let me review really briefly. For discrete time, remember that all linear time invariant systems have a difference equation. Which is why we're really interested in difference equations, that looks like this. Let's see, let me get rid of that. I just want to make this equal, so we have a bunch of y's and past weighted values of outputs, and that's equal to a bunch of inputs and past inputs that are weighted. So that's the basic difference equation for discrete time systems. When we take h of z, we end up with a rational fraction. So all linear time invariant systems can be written with a system function that's a rational fraction. It looks something like this. Okay, so there's a rational fraction of polynomials in z, numerator and denominator. We can also write this in a factored form. And I'm leaving out, there's some books, and our book in addition also puts a z to the some factor there, but that's not important for our discussion. So we have a bunch of factors. We can factor this polynomial and find its roots, and they're called zeros. And we can factor this polynomial, find its roots, and they're called poles. I'll only show two of them just to make my point. And then we can look at the magnitude by letting z equals e to the j omega and take absolute value, and we can get this into a form that sort of looks like this. So we have the product of a bunch of absolute values, and we've let z equal e to the j omega. And that's the numerator terms with the zeros. And similarly, we have e to the j omega replacing z, but we still have the pole sitting there. And we take the magnitude, because we're taking the magnitude, e to the j omega minus p2 times all of the rest of the factors there. And then when we talked about it in class, we said, you know, these complex numbers are just like vectors, and so when I take the magnitude, I'm just measuring the length of a vector. And when I take the difference of two vectors, it's just standard vector subtraction, just like in statics and dynamics. So this is stuff we know about. And in fact, if I had a ruler, I could just sit there and find these distances from the vector e to the j omega to each of the zeros. dz1, that's this distance. dz2, that's this distance. And I could multiply those all together, and then I could find the distance from the vector e to the j omega to the pole 1 and to pole 2, called dp1, dp2, ... And I can get another way to measure the frequency response. So at any given frequency omega, I measure all these distances to poles and to zeros and find the ratio, and I get the frequency response. Alright, for continuous time, story is very similar. we have all linear time invariant systems can be written as in the form of differential equations. With constant coefficients and linear differential equations, and we get these from, you remember, from Kirchhoff's voltage law or Kirchhoff's current law. We did that in 2220, and you get something in the form of these differential equations: a1 dy dt plus a2 dy second derivative plus dot dot dot. And on the right side of the equations we got b0 plus b1 dx dt plus dot dot dot. So we get this big differential equation. When we take Laplace transforms, we again get a rational function of polynomials. It's remarkable. So we get something very similar: bk s to the k over sum of weighted sum of ak s to the k. So we get a ratio of polynomials in S, and we can also write that in factored form. These are, of course, different roots, so they're different zeros. Maybe I'll put a little bar over them to make them different than the values, the zeros up there. And over S minus P1, S minus P2. So this is the factored form for a Laplace case. Well, just like in discrete time, we can find the frequency response using the same graphical technique where we're looking at the magnitude frequency response. We can also do this with phase, but we're not going to do it in this class. And the way we do that is we write it as a bunch of vector distances, but now S is equal to j omega, right? So we've got j omega minus z1, j omega minus z2, dot dot dot. That's the numerator. And in the denominator we've got j omega minus p1, j omega minus p2, dot dot dot. So we have to treat these as vectors just like before, but now we've got j omega and not e to the j omega. So you can see that the procedure is going to be very similar to that for discrete time. We take the ratio of the product of all the distances from j omega to the zeros over the distances to the poles. Alright, so just to formalize this, let me write the procedure out. You set omega equal to 0, and then we're going to increase omega with each one of these steps. So the first step is you measure the distance from S equals j omega on the j omega axis to the nearest 0. Okay? In this class we're only going to worry about only one 0 and one pole, the closest 0 and the closest pole. So we'll only get an approximation to the frequency response, and we'll kind of ignore all the rest of them. So it won't be perfect, but the whole idea of this is to get a visualization of what the frequency response is going to be by looking at the S-plane. So we're going to measure the distance from S equals j omega to the nearest pole. So this is going to be dz, and this is going to be dp. And then we're going to get our estimate of frequency response is going to be the ratio of these two guys, dz over dp. Okay, and in all of this, we're going to not worry about g. We're going to assume that this is equal to 1. Okay, so I'll draw a little purple thing around it. So we're really interested in the shape of the frequency response more than anything when we do this sort of analysis. And then once we have this value for this frequency, then we increase omega a little bit and repeat. So we're just gonna look at this ratio as we increase the frequency along the j omega axis. Okay, I had to shift, get a new piece of paper here, and I want to do one example, and then we'll be done. Let's look at a particular case, h of s, and I got it here in factored form, s times s minus 1 over s minus 1 plus j3, and s minus 1 minus j3. Okay, let's talk about this for a second. Remember that there's the first pole and there's the second pole. They're complex conjugate pairs. That will always be the case if you have a real system. Okay, and the two zeros are at s equals 0 and s equals 1. Okay, so we can write the pole 0 diagram. Let's see, we have a 0 at 0 and a 0 when s is equal to 1. I'll put that over there. So there's s equals 1. That's that 0. And we have a pole when s is equal to this thing. So there's the first pole, P1, and there's the second pole, P2, but it's equal to P1 conjugate. Alright, so it's at a real value of -1, which is good, right? Because it has to be on the left half plane. It has to be a stable system. Plus j3. So there, let's just mark these off: j1, j2, j3. So there's the j omega axis, and we come over there, and we come down there, and we have a pole at -1 plus j3. We have another pole down here at -1 minus j3, right? So that's the complex conjugate, -1 minus j3. So there's the pole 0 diagram for this system. Now, how do we get the frequency response for this simple system? Remember, don't worry too much if there's a whole bunch of poles and zeros. We're only going to look at the closest pole. So, for example, we're going to pick, according to our procedure, a small value of omega. So we're going to start at 0, and then the frequency response is the distance between the nearest 0 over the nearest pole. Difference from j omega to the nearest 0 over that to the nearest pole. So if we're starting here, the distance to the nearest 0 is 0, right? Because we're right here on the j omega axis, and there's a 0 right away. So we have to be right there on the j omega axis. 0 frequency response. As we start moving up, say we move to right here, the distance to the nearest 0, dz, is this distance, and the distance to the nearest pole is that distance. Right, so this ratio starts to get, from 0, it starts to build. And in fact, as it gets, there's at some point right about there where it's about 1, and then up here it gets, let me write this in, dp. Right at this frequency, we get the maximum ratio of dz over dp. And the reason is dp is at its smallest value at this frequency when omega is equal to 3. So when the distance of the 0 is small, or distance of the pole is smallest, that makes the frequency response the biggest. So that happens at what do we say, 3. Omega equals 3. So this thing is gonna kind of build up to some value, and then it's going to start dropping off. Eventually, as we go higher and higher omega values, the distance to the nearest zero and the distance to the nearest pole, we're going to be way up here off the top of the page. Those distances may be 100 miles and 100.1 miles. So the ratio is going to be very close to 1 as we get to higher and higher frequency values. And that's because in this particular case, the number of zeros and the number of poles are the same. So please imagine that you're way up there looking back. The distance to the zeros and the poles is all about the same. So we're going to have all the zeros distances and pole distances is going to be about equal. Now notice I'm not asking you to put in any particular values on this frequency axis. I just want to get a shape out of this. Okay, I'm sorry this is running late, so let me slip in one more quick example. I've already written it down here to save a little time since this is going so long. But basically there's the factored h of s. Here's the s-plane. We have a pole at -3, we have a 0 at -3 and a 0 at -4 shown there. We have 3 poles, a pole at -1, oops, I forgot to write that in there, it's right there, and a pole at s plus, at a pole at -2 minus j5 and -2 plus j5, which are shown there. Okay, so there's 3 poles, pole, and 2 zeros. Now again, what we would do to find the frequency response is start here and start moving up. When we're right here, the ratio, okay, the distance to the pole is very small, and when the pole distance is very small, it's in the denominator, you get a big response, and the distance to the zero is bigger. Okay, so we can imagine that, and that as we move out, we get further and further away from this pole, and very quickly, and less quickly, we get further away from this zero. So when we move away from poles, the response starts to dip. Okay, at some point the nearest pole becomes this guy. Suppose we're up here, and then the nearest zero is that guy. So there's dz, and there's dp. And as we move up here, we get sort of an increase because we get in the vicinity of this pole. Okay, important to note, this pole is far away from the j omega axis, so it has less of an impact than this pole, which is really close to the j omega axis. So what we do is we get a broad response because the pole is far away from the j omega axis. And here we get more of a sharp, I don't show it as very sharp, but I should have shown it a little bit sharper, because the pole is close to the unit, to the j omega axis. And the last thing is, as we go out to infinity, note there's more poles than there are zeros. So if we add up the products of all the zeros over the poles, this whole thing starts going towards zero. So eventually we would drop off towards zero. So this broad peak is right around 5. And this sharper peak is at 0. Okay, that concludes this very long lecture.